In this screencast, we're going to review how to assign electron configurations to elements in the periodic table. So what I've pre-drawn for us is an abbreviated version of the periodic table of the elements that are relevant to organic chemistry 1 and 2. So in red, what I've shown here are the groups, and groups are composed of the columns that run vertically in the periodic table. So we have 8 groups, and then the periods, which run horizontal in the periodic table. So the beauty of the periodic table is that we can gain a lot of information just based on where things occur in the periodic table. So for this specific screencast, we're talking about electron configuration. So we're going to start with hydrogen, and we're going to specifically work our way to carbon, because carbon's the element we're most concerned with in organic chemistry. So what I want to do in this white space of the whiteboard here is generate a table that kind of builds up electron configurations and shows how the periodic table is actually periodic and how we can get a lot of information from these trends. So in our first column here, I'm going to write atomic number. We're going to start with atomic number 1, and that's hydrogen. And the atomic number basically is equal to the number of total electrons in that element. So hydrogen has an atomic number of 1. It has 1 electron. So what is the electron configuration? So we're in period number 1. That's the first shell. So the lowest energy orbital in any shell is the s orbital. So we'll recall from general chemistry that the shape of an s orbital is spherical. And since we have 1 electron, we're going to denote that as a superscript above the s. So the electron configuration for hydrogen is 1s1. So in the first period, the next element that we encounter is helium, and we're adding 1 electron. So we have an atomic number of 2. The element is helium. We have 2 electrons. So we're going to build up from hydrogen. So we're still in the 1s orbital here. We've added a second electron. We've now filled that 1s orbital. Keep in mind that any orbital can only have 2 electrons. Now we're in period number 2. Atomic number 3 is lithium. We have 3 electrons. The first 2 electrons are going to be the configuration of helium. So we start with 1s2. Since we're in period 2, we're now in the second shell. Remember, the lowest energy orbital is the s orbital, and the third electron is going to go into that orbital. So I want to point out some relevant facts here of why these electron configurations are going to be useful when we get into Lewis dot structures. In this configuration, the 1s2 electrons are core electrons. The 2s1 electron is a valence electron. So total electron count for lithium is 3, and that's further classified into core and valence electrons. Moving to atomic number 4, which is beryllium. So see how the atomic number and electrons are the same number. This is going to have the first core electron count as lithium. So we're going to have the 1s2, the 2s1, and then the fourth electron is going to pair into that orbital. So now we've filled that 2s orbital. So we're going to go to atomic number 5, which is boron. It has 5 electrons, 1s2, 2s2. So where does the fifth electron go? Well, it's not going into 3s orbital because we're not in the third period yet. We're still in the second period. We're going to introduce a new orbital type. So that's the p orbital. So that fifth electron is going into the 2p orbital. So of the p orbitals, there are 3 types. There's px, py, and pz. These letters basically denote the axis in which that orbital lies. The orbitals themselves are all dumbbell shaped and they're degenerate. That means they're all equal energy. So if we move on to atomic number 6, that's carbon. That has 6 total electrons. 1s2, 2s2, and 2p2. So keep in mind that since each p orbital can hold 2 electrons, the 2p orbital as a whole is ultimately going to hold 6 electrons. So continuing on, 7 is nitrogen. It's 1s2, 2s2, 2p3. Eight is oxygen. The 1s2, 2s2, 2p4. So you can see the trend that's building up. We're sequentially adding electrons into this these degenerate p orbitals. So this shows how we assign electron configuration. We're going to further use this information to help us start drawing structures. And that's going to be a next screencast on Lewis dot structures.